Hi everyone, thank you for coming to my talk. First of all, I would like to thank the organizers for giving me this opportunity to present my work in this such a difficult time. I'll be talking on generalized tracking quintessence models for dark energy. So let us start. So our standard model of cosmology suffers from a key problem, explaining uh, the idea that if we are living in some special time, that means the energy density of the scalar dark energy and the energy density of the matter is comparable today. So if we consider remote past or far future, they may have differ by several hundred orders of magnitude, but the question why they are of the order of one today. So this is famous cosmic coincidence problem. Another associated problem with it is the fine-tuning problem, according to which the dark energy density is very tiny compared to the particle physics scale. So if you want to achieve a universe which looks like today, the cosmological parameters must be very fine-tuned at the beginning. So these two are the very famous problems of standard model of cosmology. So if we consider the scalar field to be the component of the dark energy, then we can find some interesting solutions which are called tracking solutions, which can alleviate these two problems discussed. And these tracking or tracker solutions are very interesting because these solutions are itself uh, will act like a attractor, which actually attract us many solutions which started from different initial conditions, and they rapidly converge to this tracker solution. And the advantage of the tracker behavior is that once the solutions converge to this attractor, those solutions actually wipe out their memory about the initial conditions. So these tracking solutions can help us to solve the problems with the fine tuning and the cosmic coincidence problem. But the problem with the tracker solution is that the potentials which are explored in the literature, uh, they cannot give us equation of state which is compatible with the present day cosmological observations. So they can track the background density and they can give us the equation of state, which is around minus 0.8, but not close to minus 0.1. So in this work, we have formulated a new generalized way to identify tracking solutions for a large class of potentials. And we showed that these solutions can give us a late time behavior which is very well consistent with the observation. And we have also considered the linear perturbations of the quintessence field. And one more thing, that we will be considering the scalar field model, which is quintessence, and with a general parameterization. So, so let us discuss about the theoretical background of this. We consider FRW metric, which is flat by considering this kappa equal to 0, and this is the basically action of the quintessence field, where action of our model, where canonical scalar field is minimally coupled to the matter Lagrangian. So if we do find out the Friedman equations, these are to the Friedman equation, this is the continuity equation, then this is the Klein-Gordon equation for the scalar field. All variables, they have the usual meaning as, and the density of the scalar field, pressure of the scalar field, and equation of state of the scalar field can be written in this following way. Where we'll be using this gamma phi for our work, which is another way of writing the equation of state of the scalar field. So here in this equation, one can see this V phi is basically arbitrary. So the potential is arbitrary. So that's a problem with the scalar field models, where you can come up with a potential and it seems that potential is consistent with the observation. So somehow the universe do not care about the form of the potential. So, can we do something to basically parameterize a large class of potentials. So we are going to spend few minutes on that topic. So basically, to do that, one need to apply a transformation, which is a polar transformation of which looks like this. And now you can see these y1 and y2 are related to the potentials, and the x and y, which is written in terms of two polar variables and the scalar field energy density. So if we do this transformation, our set of equations will reduce to this, where the derivatives are with respect to the E folding, and the scalar field energy density can be written as like this, and the equation of state of the scalar field is written like this, 1 minus cos theta. This theta is basically, that is the advantage of writing this equation in terms of polar variable, because these theta and omega phi, they have direct physical meaning. But this x and y in the Cartesian coordinate, they cannot be associated with some direct physical meaning. So now, what is the problem with the arbitrariness of the potential in this case is that the arbitrariness is now in the y2. So this set of equation is not closed until we supply a form of y2. So there are two ways to find out the particular form of y2. One can consider a potential and use these definitions of y1 and y2 and can find out y2. And otherwise, one can consider a particular form of y2 and integrate it back to get the potential, which is very, very easy. Now we have, in this work of ours, in 2018, we have used both the ways. So we consider a large number of quintessence potentials which are available in the literature, and we write down the y2 in this table. And one can see this y2 actually follow a particular pattern. So this y2 can be written in a power series like this. So if we put n equal to 2, that means alpha 0, alpha 1, alpha 2, we can get back all these potentials. So this is from v phi to y2. Now we consider the y2 and try to find out v phi. So we consider this general parameterization for n equal to 2, which looks like this. Then we consider different combination of alphas, and we just integrate it back. And we get a more general class of potentials in which the previous table is included. So consideration of this general form of the potential y2 is pretty good, because we can work with a very large class of potentials existing in the literature. So now we use this parameterization to study the background equations and their critical conditions. So we put this y2 in this form, and it can be written with a little bit mathematical manipulation. We can show that these are the three critical conditions for the system, for the background. So basically, one can find out the fixed point or the critical point from these three by solving simultaneously these three equations. But there are, in general, four classes of solution. One is fluid dominated solution, in which the equation, the scalar field energy density is 0. And another is the scaling solution, in which the scalar field equation of state is exactly the background equation of state. Another is the tracking solutions, in which basically the scalar field energy equation of state actually track the background equation of state, and the quintessence dominated state, in which the omega phi is 1. It's completely dominated by the quintessence. So we are actually interested in the tracking C, in the C, which is the tracking solution. So these are our critical conditions. So to find out simple tracking solution, let us put alpha equal to 0, alpha 0 equal to 0, alpha 1 equal to 0, and this will give us that gamma phi c is minus gamma total by 2 alpha 2. So that means gamma, the equation of state of the scalar field, is proportional to the background energy, background equation of state. So we know that gamma phi it can be between 0 and 2. 0 is the cosmological constant, and 2 is basically the steep fluid. So we can put a constant on the alpha 2 parameters, which is minus gamma total by 4. So if we want our tracking to be started at the deep in the radiation domination. So gamma total is 4 by 3. So we'll get alpha 2 must be less than minus 1 by 3. That's the condition for the tracking to be started in the radiation domination. For let us start consider an example. For the potential V pi is a power law potential. So in this case, alpha 0 equal to 0, alpha 1 equal to 0, and the P can be written in terms of this. So just comparing it with our general form of the general parameterization. Now, if we consider that alpha 2 must be 1 by 3, must be less than 1/3, minus 1/3, for the tracking, we will find that there are two conditions on C, P. P must be greater than 6, because alpha 2 must then be between less than minus 1/3 and 0.5, greater than 0.5, and if minus alpha 2 is less than minus 0.5, then P must be negative. And alpha 2 equal to minus 2 is a different class of potential, which can be seen from the table we presented before. So that's the exponential potential. So basically, this tracker condition can be satisfied for a more general class of potentials where alpha 0 and alpha 1 not equal to 0, as long as the quintessence density parameter omega phi is negligible. So if the omega phi is negligible compared to the dominant energy density, then that one can find the tracking behavior for the general case also, and which is the case at the early times. So we'll see while we're doing the numerical simulation of the model. And linear, we are also considering the linear perturbation of the system. So let us consider a perturbation of the scalar field, which looks like this phi t and phi xt, and we choose the synchronous gauge, which is this, and the linearized Klein-Gordon equation for the part of scalar field can be written in this form, and here a dot is with respect to the cosmic time, and the h is basically tensor metric perturbation, and k is the co-moving wave number. So this linearized KG equation can be written into two first order differential equations and to form a dynamical system by considering two transformation to another which looks like similar to the background, and by considering another transformation, and with some mathematical manipulation, you can show that they can be written in this form. And this delta 0 is having is the quintessence field density contrast, and the Kj is the James Webb number, which is related to y1, and the K effective can be written like this. So the y1 and y2 is in the Kj and K effective. So we have now the background equations ready, and the perturb equation of the density contrast is ready. So we want to do the numerical simulation, so we must find out some initial condition. So by considering the tracker condition, it is very easy to find a set of initial conditions which are pretty good to give us a universe as look at today. So we consider this tracker condition, and we solve the background equation for radiation domination and matter domination, and we equate them at present at the radiation matter equality, and we find out that the initial variables can be related to the present value of the cosmological parameters of the matter density, radiation density, and the dark energy density. And we consider the initial condition for the perturbation variable to be 0 at the beginning, and we amended a publicly available Boltzmann code class with all these. We implemented all these in the class code, and these are the plots. So this is the plot of the equation of state with log of the scale factor in log scale. You can show that the this is the attractor, the tracking attractor solution, and the solutions has attracted in the early time, and they have reached the tracking solution. And this blue is the lambda CDM, and one can see these different colors has different choice of the alpha parameters. So this yellow one is basically in which we have discussed about this power law potentials. This is actually basically inverse power law potential. And then we can see this is a line. Now what we do, we change the two other alpha parameters, alpha 0 and alpha 1. One can see once the alpha 0 and alpha 1 are positive, the trajectory, the solutions are bounced back, this red and green. So they cannot drive the accelerated expansion. But as we make the alpha parameters more negative, the solutions are becoming more consistent with the cosmological constant. That is the omega phi is -1. So they are approaching equation of state equal to -1. Here in this right plot, we basically plot the phase plate of omega phi and omega phi dot prime. So this is -1/9 and 0. This is 1/3 0. So this is basically the radiation domination, and this is the matter domination, and this is the cosmological constant scale. And so we can see all the trajectories have started from the radiation dominations, and they are attracted towards the matter domination, in which they actually reflected, bounce back, and the solutions, the green and red, which are having the positive alpha 0 and alpha 1, they actually bounce back to the radiation domination again. But the solutions which are having negative values of alpha 0 and alpha 1, they are basically bounce, and they are approaching omega phi to be -1. So the the cosmological constant case. So for the tracking, it is necessary in our model that we have the alpha 0 and alpha 1 negative. And these are the 2-point temperature autocorrelation function, autocorrelation power spectrum of CMB. And here you can see basically all the tracking solutions are basically can be distinguished easily from this blue line, which is the lambda CDM, and the red and green, which is again the positive alphas, alpha 0 and alpha 1. They differ more from the lambda CDM. But as the alpha parameters are becoming more negative, so they tends to more agree with the lambda CDM. And here is a mass power spectrum. It is the same thing. One can see the red and green are more different from the lambda CDM, and as the alpha parameters, alpha 0, alpha 1 become more negative, the gap between the lambda CDM and the tracking is basically a constant on our alpha parameters, and one can see this alpha 0 and alpha 1 case. They are quite inconsistent with the fact that omega phi is -1, and this is basically one can see that once you allow the alpha 0 and alpha 1 to evolve, so you can get a equation state close to -1. And this is the plot for the alpha parameters, and one can see that for a prior 0 to -10, these two plots are these alpha 1 and alpha 2 are arbitrary, and one again the alpha 2 -1/3 is alpha 2 less than -1/3 is also allowed by the data. So in this plot, we actually showed that consideration of the linear density perturbation is important for studying quintessence models. So basically, one can see that solutions are very much different from the case when we consider the linear perturbation. So one can put a misleading constant on the parameters if the linear density perturbation is not considered. And in conclusion, we have revised the case of tracker quintessence model of dark energy parameterization, and we gave a new formalism for the identification of the tracker models, which can give us a very good agreement with the late time behavior. Only one parameter alpha 2 is needed to find the tracking conditions, but where the other alpha parameters play the role to make it more realistic in the late time. And though the common wisdom not is to neglect the dark energy perturbations, we showed that they are very important. Otherwise, one can put misleading constant on the cosmological parameters. Okay, thank you.